What if I told you the biggest myth about air travel's environmental impact is about to be shattered? For years we've been told that flying is an environmental disaster with no realistic solution, that electric planes are decades away, that the only way to reduce aviation's carbon footprint is to simply fly less, that green aviation is nothing more than corporate greenwashing and wishful thinking. Forget everything you thought you knew about sustainable planes, because while the world has been debating and despairing, a quiet revolution has been taking place. Right now, at this very moment, commercial aircraft are flying passengers across continents using fuel that produces up to 80% less carbon emissions than traditional jet fuel. Not prototype aircraft, not test flights, regular commercial flights on planes you could book a ticket on today. This isn't some distant future technology requiring entirely new aircraft or airport infrastructure. This is happening now, and it's scaling faster than most people realize. Welcome to the world of sustainable aviation fuel, SAF, the cutting-edge technology that's quietly revolutionizing aviation and making truly sustainable flights a reality much sooner than you expect. Today we're going deep into the science, the economics, the challenges and the surprising benefits of the fuel that's reshaping the future of flight, because the path to guilt-free flying isn't what you think it is, and it's arriving faster than almost anyone predicted. Let's explore the fuel that's changing everything. Before we dive into solutions, we need to understand the problem, and it's significant. Aviation currently accounts for approximately 2 to 3% of global carbon dioxide emissions. That might sound small, but context matters. Aviation is one of the fastest growing sources of emissions, and it's one of the hardest sectors to decarbonize. Unlike ground transportation where electric vehicles are rapidly scaling, or power generation where renewable energy is increasingly competitive, aviation faces unique challenges. Aircraft need energy-dense fuel. They need to carry that fuel's weight for hours at high altitude. They need fuel that performs reliably at -40°C at cruising altitude, and they need global infrastructure to refuel anywhere in the world. Traditional jet fuel, essentially refined kerosene derived from crude oil, has powered aviation for decades because it perfectly meets these demanding requirements. It's energy-dense, stable across temperature extremes, relatively safe to handle, and globally available. But it's also a fossil fuel, releasing carbon that's been locked underground for millions of years into the atmosphere. The numbers are stark. A single long-haul flight from New York to London produces roughly 1 ton of carbon dioxide per passenger in economy class. Multiply that by the approximately 4 billion passengers flying annually, and aviation's climate impact becomes clear. But it's not just about carbon dioxide. Aircraft also emit nitrogen oxides, particulate matter, and water vapor at high altitude where they have amplified climate effects. When you account for these non-CO2 effects, aviation's total climate impact may be 2 to 4 times higher than CO2 emissions alone. And here's the critical issue. Demand for air travel is projected to double over the next 20 years. Emerging middle classes in Asia, Africa, and Latin America want the same mobility that developed nations have enjoyed for decades. Without intervention, aviation emissions could triple by 2050, even as other sectors decarbonize. We're already seeing the impacts. Extreme weather events are disrupting air travel with increasing frequency. Heat waves ground aircraft because hot air is less dense, reducing engine performance and lift. Severe storms and turbulence are becoming more common and more intense. Wildfires close airports and fill airways with smoke. Rising sea levels threaten coastal airports from Miami to Bangkok. The aviation industry recognizes this isn't sustainable. Airlines, manufacturers, and governments have committed to ambitious climate goals. The International Air Transport Association, IATA, has pledged to achieve net zero carbon emissions by 2050. Individual airlines have set even more aggressive targets. But pledges without pathways are meaningless. The question isn't whether aviation needs to decarbonize, it's how. Electric aircraft show promise for short regional routes, but battery energy density isn't sufficient for long-haul flights and won't be for decades. Hydrogen fuel cells are being explored, but require completely new aircraft designs and global infrastructure. These technologies will play roles in aviation's future, but they can't solve the problem alone or soon enough. This is where sustainable aviation fuel enters the equation. SAF isn't a distant future technology requiring wholesale infrastructure replacement. It works in existing aircraft, uses existing airports, and can scale with current technology. It's not the only solution aviation needs, but it's the most immediate and scalable tool available to dramatically reduce emissions now. The concept of guilt-free flying sounds idealistic, perhaps even naive. But what if it's not? What if the technology already exists to dramatically reduce aviation's climate impact without requiring passengers to stop flying or wait decades for revolutionary new aircraft? That's the promise of SAF. And it's not just promise, it's already being delivered. Let's demystify sustainable aviation fuel. What is it, how is it made, and how does it differ from the kerosene currently powering aircraft? At the molecular level, SAF is nearly identical to conventional jet fuel. It's composed primarily of hydrocarbons, molecules made of hydrogen and carbon atoms, just like fossil-based kerosene. When it burns in an aircraft engine, it produces thrust, heat, water vapor, and carbon dioxide, just like conventional fuel. So what makes it sustainable? The critical difference is where the carbon comes from. Conventional jet fuel releases carbon that's been sequestered underground for millions of years, adding new carbon to the atmospheric cycle. Sustainable aviation fuel uses carbon from sources that are part of the current carbon cycle, carbon that was recently in the atmosphere and will return there, but doesn't add new fossil carbon to the system. Think of it this way. Burning fossil fuels is like withdrawing from a geological savings account of carbon that's been locked away, adding to the atmosphere's carbon balance. Burning SAF is more like recycling carbon that's already in circulation. SAF can be produced from an incredibly diverse range of feedstocks, and this diversity is one of its greatest strengths. Used cooking oil is one of the most common current feedstocks. Restaurants, food processing facilities, and commercial kitchens generate enormous quantities of waste cooking oil. Instead of disposing of this waste, it can be collected and converted into jet fuel through processes like hydroprocessed esters and fatty acids, or HEFA. This pathway is proven, scalable, and is producing significant volumes of SAF today. Agricultural residues offer another pathway. Corn stalks, wheat straw, rice husks, sugarcane bagasse. These crop residues are typically burned in fields or left to decompose. Instead, they can be collected and converted into SAF through processes like Fischer-Tropsch synthesis or alcohol-to-jet pathways. This doesn't compete with food production because it uses the parts of crops that aren't eaten. Forestry waste and woody biomass provide additional feedstock, waste from timber operations, diseased trees removed for forest health, and dedicated energy crops grown on marginal land unsuitable for food production can all be converted to SAF. Municipal solid waste, your household garbage, can be processed to extract organic materials and convert them to fuel. Rather than sending waste to landfills where it produces methane, a potent greenhouse gas, that waste can be transformed into jet fuel. Even more innovative are power-to-liquid or e-fuel pathways. These processes capture carbon dioxide directly from the atmosphere or from industrial sources, combine it with hydrogen produced from renewable electricity through electrolysis, and synthesize liquid hydrocarbons. This pathway essentially creates fuel from air, water, and renewable energy. While currently expensive and energy-intensive, it represents enormous potential as renewable energy becomes cheaper and more abundant. The production processes vary depending on feedstock, but they generally involve breaking down the source material, purifying and processing it, and then synthesizing it into hydrocarbons that meet stringent aviation fuel specifications. And here's what makes SAF a game changer. It's a drop-in fuel. This term means SAF can be blended with conventional jet fuel and used in existing aircraft without any modifications to engines, fuel systems, or airport infrastructure. You don't need new planes. You don't need new pipelines or storage tanks. You don't need to retrain mechanics or pilots. SAF meets exactly the same technical specifications as conventional jet fuel, ASTM D7566 in the United States, or equivalent international standards. Currently, SAF is typically blended up to 50% with conventional fuel, though this limit is based on certification requirements rather than technical limitations. Airlines and fuel producers are working toward approving 100% SAF use, and some flights have already operated on 100% SAF during demonstration and certification testing. This drop-in nature is crucial because aviation infrastructure represents trillions of dollars of investment and decades of development. Any solution requiring complete infrastructure replacement would take decades to implement and cost astronomical sums. SAF leverages all existing infrastructure while delivering immediate emissions reductions. The life cycle emissions reduction from SAF varies depending on feedstock and production pathway, but typical reductions range from 50 to 80% compared to conventional jet fuel. Some pathways can achieve even greater reductions, potentially reaching 90% or more. This calculation considers the entire life cycle, growing or collecting feedstock, transporting it to processing facilities, converting it to fuel, distributing it, and finally burning it in aircraft engines. While combustion still produces CO2, that carbon was recently captured from the atmosphere by plants or other processes, rather than being fossil carbon added to the system. It's important to note that SAF isn't carbon neutral in absolute terms. There are energy inputs, transportation emissions, and process emissions associated with production, but the life cycle emissions are dramatically lower than conventional fuel. And as production processes improve, and renewable energy powers more of the supply chain, emissions will continue declining. SAF represents the most practical, scalable near-term solution to dramatically reduce aviation's carbon footprint using technology that's proven, certified, and already in commercial operation. Most discussion about SAF focuses exclusively on carbon emissions reduction, and while that's certainly the primary driver, SAF offers numerous additional benefits that are often overlooked but equally compelling. Let's start with local air quality around airports. Anyone living near a major airport knows that aircraft operations create noise and air pollution. While SAF doesn't address noise, it significantly improves air quality. When SAF burns, it produces fewer particulate matter emissions and fewer sulfur compounds compared to conventional jet fuel. These pollutants contribute to respiratory problems, cardiovascular disease, and reduced air quality in communities surrounding airports. Studies have shown that SAF can reduce particulate matter emissions by 50 to 70% and essentially eliminate sulfur emissions. For the millions of people living and working near airports, this represents a tangible health benefit that extends beyond global climate considerations. Improved air quality also benefits airport workers, ground crew, maintenance personnel, refuelers, who work in close proximity to aircraft and are regularly exposed to exhaust emissions. Reducing their exposure to harmful particulates and chemicals directly improves occupational health and safety. Now, let's discuss economic opportunities. The transition to SAF isn't just an environmental imperative, it's an economic opportunity creating entirely new industries and employment. SAF production facilities require construction, operation, and maintenance. Each biorefinery represents hundreds of millions of dollars in investment and creates skilled jobs in engineering, operations, quality control, and management. Feedstock collection and processing creates agricultural and forestry employment. Farmers growing dedicated energy crops or collecting agricultural residues gain additional income streams. Waste management companies develop new business lines collecting used cooking oil and organic waste. The entire supply chain, feedstock logistics, fuel production, quality assurance, distribution, requires workforce development and job creation. These are skilled, well-paying positions in manufacturing, engineering, and operations that can't be outsourced. Regions investing early in SAF production gain competitive advantages. They attract aviation industry investment, develop expertise, and position themselves as leaders in a growing global market. Countries like Sweden, the Netherlands, and the United States are already seeing economic benefits from early SAF investments. The global SAF market is projected to grow exponentially over the coming decades, potentially reaching hundreds of billions of dollars annually by mid-century. Companies, regions, and countries positioning themselves now will capture significant economic value. Energy security represents another critical but underappreciated benefit. Aviation currently depends almost entirely on petroleum-based jet fuel produced from crude oil. This creates vulnerabilities to oil price volatility, geopolitical instability in oil-producing regions, and supply disruptions. SAF diversifies aviation's energy sources. Feedstocks can be grown or collected domestically, reducing dependence on imported oil. This enhances national energy security and insulates airlines from geopolitical events affecting oil markets. During the Russian invasion of Ukraine, oil prices spiked dramatically, causing severe financial stress for airlines. Countries with domestic SAF production would be less exposed to such shocks. Military applications also benefit from fuel that can be produced domestically, rather than depending on potentially vulnerable supply chains. Price stability is another advantage. While SAF is currently more expensive than conventional fuel, it's less exposed to oil market volatility. As production scales and fossil fuel prices potentially rise due to carbon pricing or resource depletion, SAF becomes increasingly cost-competitive with more predictable long-term pricing. There are also innovation spillovers. Technologies developed for SAF production have applications beyond aviation. Processes for converting biomass to liquid fuels, carbon capture and utilization, and advanced catalysis benefit other industries. Research and development in SAF accelerates broader progress in sustainable chemistry and renewable fuels. Finally, there's the reputational and social license benefit for aviation. The industry faces increasing pressure from environmentally conscious consumers, investors demanding ESG, environmental, social and governance, performance, and governments imposing carbon pricing or emission regulations. Airlines investing in SAF demonstrate tangible climate action beyond pledges and aspirations. This maintains public support for aviation and prevents more draconian regulatory interventions that might severely constrain the industry. Corporate travel policies increasingly consider carbon footprint. Companies committed to sustainability are scrutinizing their business travel emissions. Airlines offering SAF options become preferred carriers for climate-conscious corporate clients. Investment funds are divesting from high-carbon industries and seeking sustainable opportunities. Airlines with credible decarbonization strategies including SAF deployment attract capital more easily and potentially at lower costs. The benefits of SAF extend far beyond carbon accounting. Improved air quality, economic development, energy security, technological innovation, and maintaining aviation's social license all represent compelling reasons to accelerate SAF adoption, even independent of climate considerations. If SAF is so beneficial and technologically ready, why isn't it already powering most flights? The challenges are real and significant, though not insurmountable. The fundamental challenge is the classic chicken and egg problem, scaling production to meet demand while achieving cost competitiveness. Currently, SAF costs approximately 2 to 4 times more than conventional jet fuel. Exact pricing varies by feedstock, production pathway, region and market conditions, but the premium is substantial. For airlines operating on razor-thin profit margins, this cost difference is prohibitive without policy support or carbon pricing that reflects the true environmental cost of fossil fuels. Why is SAF so expensive? Several factors contribute. Production facilities require significant capital investment, feedstock collection and logistics add costs, production volumes are still relatively small, so economies of scale haven't been achieved, and conventional jet fuel benefits from over a century of infrastructure development and optimization that makes it artificially cheap by not accounting for environmental externalities. Here's the chicken and egg dynamic. Airlines want to buy more SAF, but only if prices approach conventional fuel levels. Producers want to build more facilities and scale production, which would lower costs, but only if they have guaranteed long-term demand. Without demand certainty, investing billions in production capacity is risky. Without supply certainty, airlines can't commit to SAF purchases. Breaking this cycle requires either policy intervention, mandates, incentives, or carbon pricing, or voluntary corporate commitments large enough to justify production investment. Feedstock availability represents another constraint. While we've discussed diverse feedstock options, actually securing sufficient quantities sustainably is challenging. Used cooking oil, currently a primary feedstock, has limited global availability. Agricultural residues must be collected efficiently, without degrading soil health. Dedicated energy crops require land that doesn't compete with food production or displace natural ecosystems. Estimating sustainable feedstock availability is complex and contested. Some studies suggest sufficient feedstock exists globally to produce enormous quantities of SAF. Others argue that sustainability constraints, logistical challenges, and competing uses limit realistic potential. The truth likely lies somewhere between, depending on technological development and land use decisions. There's also the build-out timeline. Even with investment decisions made today, constructing SAF production facilities takes years. Securing permits, obtaining financing, completing construction, commissioning and testing, and ramping to full production is a multi-year process. Current global SAF production is measured in tens of millions of gallons annually. Total jet fuel consumption globally is approximately 90 billion gallons annually. Bridging that gap requires thousands of new production facilities. Policy and regulatory frameworks vary dramatically across countries, creating complexity for a global industry. The European Union has mandated increasing SAF blending requirements through the Refuel EU Aviation Initiative, requiring 2% SAF by 2025, increasing to 70% by 2050. The United States offers tax credits and incentives, but lacks federal mandates. Other countries have different approaches or no policies at all. This patchwork creates challenges. Airlines operate globally but face different SAF availability, costs, and regulatory requirements in different regions. Fuel purchased in one country must work seamlessly with aircraft flying worldwide. Harmonizing international standards and policies would accelerate adoption. Certification and quality assurance are critical. SAF must meet identical specifications to conventional fuel. Each production pathway and feedstock combination must undergo rigorous testing and certification before approval. This process is expensive and time-consuming but absolutely necessary for safety. There are also infrastructure considerations. While SAF is drop-in compatible, it still requires blending facilities, storage, and distribution logistics. Airports must be able to receive, store, and dispense SAF or SAF conventional blends. This infrastructure exists for conventional fuel, but must be adapted or expanded for SAF. Despite these challenges, breakthrough technologies on the horizon offer tremendous promise. Direct air capture combined with power-to-liquid synthesis could eventually produce unlimited SAF using only atmospheric CO2, water, and renewable electricity. While currently expensive and energy-intensive, costs are declining rapidly. As renewable electricity becomes cheaper and more abundant, this pathway becomes increasingly viable. Companies like Carbon Engineering and Climeworks are scaling direct air capture technology. Others like Prometheus Fuels and Infinium are developing power-to-liquid processes. These technologies could eventually produce SAF anywhere with renewable energy and air, eliminating feedstock constraints entirely. Advanced biofuels using novel feedstocks and production pathways continue developing. Algae-based fuels have long been researched and are approaching commercial viability. Municipal solid waste conversion is scaling. Even carbon-negative pathways capturing more CO2 than they emit are being demonstrated. Synthetic biology and metabolic engineering are creating microorganisms that convert simple sugars or even CO2 directly into hydrocarbon fuels. While early stage, these biological pathways could dramatically reduce production costs and expand feedstock flexibility. Process improvements in existing pathways are steadily reducing costs and improving efficiency. Every generation of HEFA or Fischer-Tropsch facilities improves on previous ones, catalysts become more efficient, energy integration reduces process emissions, yields improve. These incremental gains compound over time into substantial cost reductions. The pathway forward requires simultaneous action on multiple fronts, scaling existing proven technologies to achieve cost reductions through volume, investing in breakthrough technologies that could transform the economics, implementing supportive policies that bridge the cost gap during the transition, and creating long-term demand signals that justify massive production investment. This isn't a simple or quick process, but it's already underway, accelerating faster than most predicted even 5 years ago. The question isn't whether SAF will power aviation's future. It will. The question is how quickly and how extensively, and the answer is, sooner and more than you probably think. Let's look at real-world examples of airlines already using SAF and their commitments for the future. United Airlines has been the most aggressive U.S. carrier, operating regular SAF-powered flights from Los Angeles, San Francisco, and other hubs. They've committed to purchasing billions of gallons of SAF over the coming decades and have invested directly in SAF producers to help scale production. In Europe, KLM has been a leader, operating SAF-fueled flights and committing to 10% SAF usage on all flights from Amsterdam by 2030. British Airways is building a major SAF production facility in the UK. Lufthansa, Air France, and other European carriers have similar commitments driven partly by EU mandates. Asian carriers are accelerating adoption. Singapore Airlines, Cathay Pacific, ANA, and others are incorporating SAF into operations and setting ambitious targets. Even cargo carriers like FedEx and UPS are investing heavily in SAF to reduce emissions from their extensive flight operations. These aren't token gestures or PR exercises. Airlines are signing long-term purchase agreements worth billions of dollars, taking equity stakes in SAF producers, and building SAF considerations into fleet planning and route decisions. Corporate customers are driving demand too. Companies like Microsoft, Amazon, and numerous others are purchasing SAF credits to offset emissions from employee business travel. This creates additional demand signals that help justify production investment. Several airports are becoming SAF hubs: Schiphol in Amsterdam, LAX in Los Angeles, San Francisco International, and others are establishing SAF supply chains and encouraging increased usage. So, what's the timeline for widespread adoption? It varies by region and depends on policy decisions, investment flows, and technological progress. In Europe, regulatory mandates ensure SAF will reach 2% of total jet fuel by 2025, 6% by 2030, and 70% by 2050. These are legal requirements, not aspirational goals, meaning the infrastructure and production must be built to comply. In the United States, the Biden administration has set a goal of 3 billion gallons of annual SAF production by 2030, and sufficient SAF to meet 100% of aviation fuel demand by 2050. While these are targets rather than mandates, they're backed by tax credits, research funding, and policy support. Globally, IATA's commitment to net zero by 2050 assumes that 65% of emissions reduction comes from SAF. This requires SAF to comprise approximately 65% of total jet fuel by mid-century. For the average traveler, this means that within the next decade, a significant portion of flights, especially on certain routes and from certain hubs, will be partially or fully powered by SAF. You're likely to fly on SAF in the next few years if you haven't already, even if you're unaware of it. Some airlines are offering passengers the option to pay a premium for SAF-powered flights or to purchase SAF credits offsetting their travel emissions. While currently expensive, this allows environmentally conscious travelers to support SAF development and fly with reduced guilt. Looking to 2030 and beyond, SAF will transition from niche to mainstream, production will scale dramatically, costs will decline toward parity with fossil fuel, especially as carbon pricing makes fossil fuels more expensive. More feedstocks and production pathways will come online, and flights powered significantly or entirely by SAF will become routine rather than noteworthy. By mid-century, if current trajectories continue, the majority of aviation fuel could be sustainable, with remaining emissions addressed through emerging technologies like hydrogen aircraft on shorter routes and carbon removal for residual unavoidable emissions. This isn't guaranteed. It requires sustained investment, supportive policies, technological progress, and collective commitment, but the momentum is building rapidly. Now, what can you do as a consumer or citizen to accelerate this transition? First, stay informed and demand transparency. Ask airlines about their SAF usage and commitments. Choose carriers investing in sustainability when practical. Support isn't just about avoiding flying, it's about supporting the airlines making genuine efforts to decarbonize. If you fly frequently for business, encourage your employer to prioritize airlines using SAF or to purchase SAF credits for corporate travel. Many companies want to reduce travel emissions but need employee engagement to prioritize this. Support policies that accelerate SAF adoption. Carbon pricing, clean fuel standards, production incentives, and blending mandates all help scale SAF. Contact elected representatives to express support for climate-friendly aviation policies. Recognize that sustainable aviation requires accepting higher costs during the transition. SAF premiums, carbon pricing, or environmental fees will likely increase ticket prices in the near term. This is necessary to fund the transition and reflect aviation's true environmental cost. Invest in or support companies developing SAF technologies if you have investment capital. The SAF industry needs patient capital willing to fund development, demonstration, and early commercial deployment before technologies reach full competitiveness. Advocate for research funding. Government-supported research into advanced biofuels, power-to-liquid synthesis, and breakthrough technologies accelerates progress in ways markets alone won't achieve. Perhaps most importantly, maintain a balanced perspective. Aviation enables global connection, economic development, and cultural exchange. The goal isn't to eliminate flying but to make it sustainable. SAF offers a path forward that preserves aviation's benefits while dramatically reducing its climate impact. The narrative around aviation and climate has often been binary. Either accept unacceptable emissions or stop flying entirely. SAF provides a third path. Transform aviation's fuel source and fly guilt-free without abandoning global mobility. This transformation is underway right now. Production is scaling, airlines are committing, Policies are driving adoption, technologies are improving, the future of flight is being written, and it's powered increasingly by sustainable fuel. We open this video by challenging the biggest myth about aviation's environmental impact, that there's no realistic solution to make flying sustainable. We've explored how sustainable aviation fuel shatters that myth. It's not a distant dream or speculative technology. It's real, it's certified, it's flying right now, and it's scaling rapidly. SAF reduces life cycle carbon emissions by 50 to 80% or more. It improves local air quality around airports. It creates economic opportunities and green jobs. It enhances energy security. And it works with existing aircraft and infrastructure, enabling immediate impact without waiting for revolutionary new technologies. Yes, challenges remain. Costs are higher than conventional fuel. Production must scale dramatically. Feedstock supply chains need development. Policies must support the transition, but these are solvable problems, and solutions are actively being implemented. The timeline is aggressive but achievable. Significant SAF adoption within this decade, majority SAF usage by mid-century, and continuous improvement in production efficiency, feedstock diversity, and emissions performance. The future of aviation isn't electric planes that won't exist for decades, or hydrogen aircraft requiring entirely new infrastructure. Those technologies will play roles, particularly on shorter routes, but SAF is the immediate scalable solution that's already transforming how we fly. Every time you board an aircraft in the coming years, there's an increasing chance you're flying on sustainable fuel. The revolution is quiet but profound. The technology is proven, the momentum is building. The skies aren't closed to sustainable travel, they're opening wider than ever, powered by innovation that's turning waste into flight, carbon cycles into propulsion, and environmental challenge into economic opportunity. Guilt-free flying isn't a myth, it's not marketing greenwash, it's an achievable future being built right now by scientists, engineers, entrepreneurs, policymakers, and airlines committed to preserving both aviation and the planet. The future of flight is sustainable, and that future is arriving sooner than almost anyone expected. Thank you for exploring the cutting edge of aviation fuel technology with me. The next time you fly, remember, you might already be experiencing that future, and if not yet, you soon will be. Fly sustainable. The technology is here, the commitment is real, the transformation is underway.